We study in statistics about various measures for different characteristics of populations, such as mean, variation, skewness, kurtosis, correlation, etc. Have you ever thought that in developing all these measures, what common procedure has been adopted? That is standardization. Let us review today these measures from this point of view. I hope it would be interesting to you and would give you a new insight in these measures. Standardization means putting different variables on the same scale. This process allows us to compare scores between different types of variables. In statistics, we develop measures for measuring various population characteristics. For measuring a population characteristic, population units are measured in some unit. So, for two or more than two populations, their characteristics cannot be compared on the basis of measurements done in different units. For making these measures comparable, we have to make them unit-free. It would give you a pleasant surprise to find that in almost all the statistical measures, the effort is to standardize them so that their values can be made comparable. I would like to discuss today only some of such statistical measures other than beta coefficients, which we have already discussed previously. The first one is coefficient of variation. All of us know that a standard deviation is a measure of dispersion. It measures the amount of dispersion, or in other words, we can say amount of variation in a data set. Among all the measures of dispersion, a standard deviation is the most widely used measure of dispersion due to its various merits. It is usually denoted by capital S and is defined as the positive square root of the mean of the squares of the deviations from mean. That is, S is equal to positive square root of 1 by n summation xi minus x bar whole square. Its square, S square, is called variance. If the value of standard deviation is small, then it indicates that there is less variation in data set. If it is high, it indicates that there is large variation in data set. And if it is zero, it indicates that there is no variation at all in the data set. All the values in the data set are the same. Standard deviation has one very interesting property. It is independent of change of origin, but it is not independent of change of scale. This means that if a constant value is added or subtracted from all the values in the data set, the value of a standard deviation remains unchanged. It remains unaffected. But if all the values in the data set are multiplied or divided by some constant value, the value of a standard deviation changes. The value of a standard deviation in this case gets accordingly multiplied or divided by the same constant value. For example, the values of a standard deviation of the data set 1, 2, 3, 4, and 5 is 1.4142. The standard deviation of the data set 11, 12, 13, 14, and 15. It is also 1.4142 because here change of origin has been made. A constant value 10 has been added to all the values in the data set 1, 2, 3, 4, and 5. Similarly, the standard deviation of 10,001, 10,002, 10,003, 10,004, and 10,005 would also be 1.4142 because in this case also change of origin has been made. A constant value 10,000 has been added to each of the values in the data set. Whereas the standard deviation of 10, 20, 30, 40, and 50, it would be 14.1420 because here change of scale has been done. All the values in the data set, original data set 1, 2, 3, 4, and 5 have been multiplied by a constant value 10. And these values have become 10, 20, 30, 40, and 50. Here change of scale has been done. So the standard deviation would also be multiplied by the same constant 10. And it would become 14.1420. If we multiply all the values of the data set, original data set 1, 2, 3, 4, and 5 by 20, so we would get the values as 20, 40, 60, 80, and 100. And the standard deviation of this data set would be 28.2840 because the standard deviation is also multiplied by the same constant value 20. Here change of a scale has been done. Now, you see, it is clear that the standard deviation of 10,001, 10,002, 10,003, 10,004, and 10,005 is the same as that of the data set 1, 2, 3, 4, and 5. And that is 1.4142. Not only this, a standard deviation of 1 lakh 1, 1 lakh 2, 1 lakh 3, 1 lakh 4, and 1 lakh 5 would also be same, 1.4142. Now, one question arises here. Is the amount of variation same in all these data sets because their standard deviation is same? Standard deviation is the same for these data sets And so, on this basis, it prompts us to believe that the amount of dispersion is same in all the data sets. But how the variation can be said to be the same in these data sets? I do not agree. I can't get myself convinced. I refuse to accept it. Even a layman would not be convinced. What whatever argument you may give on the basis of your knowledge of statistics, that would not be convincing. You see, in data set 1, the minimum value is 1 and the maximum value is 5. The value has increased 5 times. In the data set 2, the minimum value is 1 lakh 1 and the maximum value is 1 lakh 5. Can an increase of 4 in 1 be the same as an increase of 4 in 1 lakh 1? Let us also take it in this way. Suppose a beggar expects 1 rupee from you, and instead you give him 5 rupees. He would be very glad. Would a person whom you have to give 1 lakh 1 rupees and you give him 1 lakh 5 rupees instead have the same pleasure as that beggar gets? Certainly not. Then how can we say that variation in both the data sets is the same? So we find that although standard deviation is a very good measure of variation, we cannot compare variation in two or more than two data sets on the basis of the values of standard deviation. The values of standard deviation are not comparable. Therefore, there is a need of a measure on the basis of which variation in two or more than two data sets can be compared. We need a measure which takes into account whether the data are big or data are small. Such a measure is coefficient of variation. It is defined as a standard deviation by mean. Generally, it is expressed in percentage as a standard deviation by mean into 100. This measures variation in data sets assuming that the mean is 100. So, all the data sets are brought on the same scale, having mean of each data set as 100. Now, whether data are small or big, that problem has gone. Now it is comparable. Not only this, it has become unit free, as the unit of a standard deviation and mean is the same. And so when we take their ratio, unit in numerator and that in denominator are cancelled out. Now let us take another measure, which is known as Bowley's coefficient of skewness. We know that in a perfectly symmetric distribution, the quartiles would always be equidistant. The difference between Q2 and Q1, that is the second quartile and the first quartile, that is Q2 minus Q1, should be same as the difference between Q3 and Q1. Sorry, Q3 and Q2. That is Q3 minus Q2. So we can say that for symmetric distribution, Q2 minus Q1 is equal to Q3 minus Q2. If these differences are not same, it means that there is departure from symmetry. In other words, there is skewness in the distribution. Thus, Q3 minus Q2 minus Q2 minus Q1 can be taken as a measure of skewness. If it is 0, it means that there is no skewness. If it is positive, greater than 0, it means that there is positive skewness. And if it is negative, there is negative skewness. But it has one defect. It is not unit free, and so is not comparable. To make it unit free, we divide it by Q3 minus Q2 plus Q2 minus Q1 and get the coefficient as Sk. This is the coefficient of skewness, symbol for the coefficient of skewness. So Sk is equal to Q3 minus Q2 minus in bracket Q2 minus Q1 divided by Q3 minus Q2 plus Q2 minus Q1, which can be expressed as Q1 plus Q3 minus 2Q2 divided by Q3 minus Q2. So the only purpose of dividing by Q3 minus Q2 plus Q2 minus Q1 is to make it unit free so that it can be used for comparing skewness in two or more than two data sets. Let us take the next measure of skewness, which is known as Karl Pearson's coefficient of skewness. We know that in case of a symmetric distribution, Mean is equal to median is equal to mode. All three coincide at the same point. In other words, we can say that for a symmetric distribution, mean minus mode is equal to 0. Mean minus median is equal to 0. If this difference deviates from 0, the distribution departs from symmetry and becomes skewed. So this difference can be taken as a measure of skewness. Again, it is not unit free. It is not standardized. To make it unit free, to make it a standardized measure, it is divided by the standard deviation. So we get the Karl-Pearson's coefficient of skewness as mean minus mode by standard deviation. We also know that if in a distribution mean is greater than median, is greater than mode, then the distribution is positively skewed. If mean is less than median, less than mode, then the distribution is negatively skewed. So the value of Sk, that is the value of the Karl-Pearson's coefficient of skewness, would be positive in case of positive skewness. It would be negative in case of negative skewness. Now let us take the next measure, Karl-Pearson's product moment correlation coefficient. All of us know correlation coefficient very well. It measures the degree of relationship. Of course, linear relationship between two variables. The extent of relationship between two variables, say x and y, can be measured by covariance between x and y. Covariance xy is defined as expectation of x minus expectation x into y minus expectation y. If the two variables are linearly independent, its value would be 0. If they are positively correlated, its value would be positive. And in case they are negatively correlated, its value is negative. This only might have been considered as the measure of correlation coefficient. But as it is not unit free, it contains unit of x as well as of y. We cannot compare the extent of relationship between two or more than two pairs of variables. To make it comparable, we would have to make it unit free. Free from the unit of x and free from the unit of y. This is done by dividing it by a standard deviation of x and by the standard deviation of y. In this way, the units of x and y would be cancelled out. This is why correlation coefficient is defined as R equal to covariance xy divided by Sx, that is a standard deviation of x, into Sy, that is a standard deviation of y. Have you ever tried to find out that in most of the test statistics, in tests of significance, such as test of a single mean, test of equality of two means, test of correlation coefficient, test of regression coefficient, etc. We just take the difference between the sample value and the assumed population value. And we try to find out whether this difference is significant or it is just due to chance. In all such test statistics, you would find this factor common. But the variables we are dealing with might have been measured in different units. To make the test statistics unit free, we standardized them by dividing the difference by the standard error of the sample value. That is, the standard error of the statistic. Once it is divided by the standard error, the test statistics become unit free. Now, next we would meet very soon with some other topic. Thank you very much. Thank you.